Hello, this is FlippedHarber for Precalculus. In this video we'll cover section 3.3, Rational Functions. Our objectives for this lesson are to find the domain of a rational function, determine the vertical asymptotes of a rational function, determine the horizontal or oblique asymptotes of a rational function, and analyze the graph of a rational function. Our topics include rational functions, their domain and range, vertical, horizontal, and oblique asymptotes. The outline for this video will start by talking about what a rational function is, the domain of rational functions. We'll look at one rational function, f of x equals 1 over x squared, and transformations to its graph. We'll talk about the three types of asymptotes. We'll look at a theorem for locating vertical asymptotes, another theorem, finding horizontal asymptotes or oblique asymptotes, graphing rational functions, and we'll look at an application, the average cost functions. A rational function is a function made up of two polynomial functions, p of x and q of x, where they're divided. The only limitation is that q of x is not the zero polynomial, which makes sense because it is a fraction after all. Now our domain is limited because it's a fraction. Because p and q are polynomials, we can plug any number we want into them. But because it's a rational function, because we're trying to divide by q, we cannot plug in anything that might make q 0. So the domain of the rational function is all real numbers except those for which the denominator q is 0. Let's take a look at our first rational function, f of x equals 1 over x squared. Now we're going to use our basic rules for transformations to move this graph around. We can see the graph here made on a calculator. Now I'm going to go ahead and shift this graph right 2 and up 3. And I accomplish this just like I have done transformations up to this point with any type of function. I subtract 2 inside with the x, and I add 3 onto the end. Here we can see the original function 1 over x squared and the new transformed function. Now let's use this function to also talk about our three types of asymptotes, or really we're going to use it to talk about two. We see here that this graph has a vertical asymptote at the y-axis. Not all vertical asymptotes are the y-axis, but this one is. Now you should remember that asymptotes are lines that the graph never actually gets to, never actually crosses. So no matter how far up we move, these lines get forever closer and closer to the y-axis, but never touch, never cross it. This graph also has a horizontal asymptote at the x-axis. Again, not all horizontal asymptotes are at the x-axis. This one just happens to be there. Now again, the curves get forever closer to the x-axis, but never touch it and never cross it. As we move farther and farther over to the right, the graph gets closer and closer and closer, but it never actually reaches y equals 0, the x-axis. And that's actually how we find horizontal asymptotes, is we plug in really large numbers for x, and we see where the graph is headed. Now this graph does not have an oblique asymptote. This one does. An oblique asymptote is a straight line, usually in the y equals mx plus b form, that the graph forever approaches, but never touches, never crosses. Now, we'll talk about some certain conditions that you have to have in order to get an oblique asymptote. Not all graphs have to have asymptotes. If they do have a horizontal asymptote, they can't have an oblique asymptote. If they have an oblique, they can't have a horizontal. Alright, let's talk about a theorem for locating vertical asymptotes. This is straight out of the book, a rational function r of x equals p of x divided by q of x in lowest terms. We'll talk about what that means in a second. We'll have a vertical asymptote x equals r if x minus r is a factor of the denominator q. That is, if r is a 0 of the denominator of a rational function, then r will have a vertical asymptote at x equals r. Now first of all, let me try to reword this. If you can plug in a number and get 0 on the bottom of the fraction, you might have a vertical asymptote there. Now why do I say might? Well, that gets back to the lowest terms idea here. Before you start to find vertical asymptotes. Try to factor the top and bottom of the rational function and cancel anything that you can. That's what it means to be in lowest terms. Just like you would reduce 2/4 to 1/2, you can do the same thing with rational functions. You factor the polynomials top and bottom and cancel anything that you can. Any factors that are left over on the bottom will create vertical asymptotes. Now, let's take a look at two very similar equations that create very different graphs. On the left, we have f of x equals x squared minus 1 all divided by x minus 1. Now, this graph does not have a vertical asymptote at x equals 1. Even though if I try to plug 1 into the function, I get 0 on the bottom, there is not a vertical asymptote. We'll talk about why in a second. The second function, x squared minus 1 all over x minus 2, does have a vertical asymptote at x equals 2. The reason that it has a vertical asymptote and the other one doesn't is because the first function is not in lowest terms. I can actually factor the top into x minus 1 times x plus 1 and cancel the x minus 1s. In the second function, even though I can factor out the top, nothing cancels. So that polynomial, that rational function, is in lowest terms. So yes, if I try to plug in 2, I get 0 on the bottom, and it creates a vertical asymptote. So don't forget, when you're trying to find vertical asymptotes, always make sure that your rational function is in lowest terms. Alright, let's talk about a theorem about horizontal asymptotes. If a rational function is proper, we'll talk about what that means in a second, the line y equals 0 is a horizontal asymptote of its graph. Now what proper means is that you have a lower power in the polynomial on top than in the polynomial in the bottom. Let's make an analogy here. When you were first learning about fractions, you learned about proper and improper fractions. 2/3 is a proper fraction because the smaller number is on top. 3/2 is improper because the smaller number is on bottom. It's the same idea here, except we're talking about powers. So if you see a proper rational function, you know that it has a horizontal asymptote at y equals 0. Well, what if it isn't a proper rational function? What if it's improper? That means that the power on top is higher or equal to the power on bottom. We need to actually use long division to find the horizontal or oblique asymptotes. Again, a graph can have either horizontal or oblique asymptotes. It's not going to have both. So here's a tip before we get started. If the powers match, now I'm talking powers top and bottom, it has a horizontal asymptote at some line y equals b. So that's a horizontal asymptote if the powers on top and bottom are the same. If the power on top is 1 higher than the power on bottom, then the graph has an oblique asymptote. That line is going to be y equals mx plus b, or something like that. If the power on top is more than 1 greater, maybe it's x to the 4th on top, x squared on bottom, then that graph is not going to have a horizontal or an oblique asymptote. Now again, I'm talking about graphs in lowest terms, so make sure you cancel anything you can before this process. Alright, so let's actually try this. Here is an improper rational function. The powers on top and bottom match. According to my tip that I just told you, this will have a horizontal asymptote. Where is it though? Well, if I actually do the long division, I can figure that out. So I'm going to take the 3x plus 5 and divide it by x minus 6. Now, I know that's actually a square root symbol. It's all my computer could type. Deal with it. So, remember, when you're doing long division like this, focus on just the x from the x minus 6. Always only focus on the first term on the outside, and only focus on one term at a time inside. So I'm looking at the 3x from inside, and I'm dividing by the x on the outside. I get 3. I'm going to multiply that around through the x minus 6, and I'm going to subtract. So 3 times x minus 6 is 3x minus 18. I subtract that from 3x plus 5, and I get 23. Now, I stop with my long division because now what I've got is a power that's lower than the power on bottom. So that 23 is a remainder. And what it means is that my rational function is actually equal to 3 plus 23 over x minus 6. Now that fraction at the end is proper. And when I'm talking about horizontal asymptotes, I'm talking about a value that the function takes at really big values for x. Well, if I plug a really big value for x into that fraction, basically it goes to 0. So what I'm left with is the 3. And that, ladies and gentlemen, is the horizontal asymptote for this rational function. Okay, let's try that again with a different rational function. Now in this case, my power on top is 4, my power on bottom is 3. According to that thing that I showed you a little while ago, this should create an oblique asymptote. Whenever the power on top is 1 higher than the power on bottom, you're going to get an oblique asymptote. Let's do our long division. So again, I set up 3x to the 4th plus 4 inside, x cubed plus 3x outside. I look at just one term at a time. I look at the 3x to the 4th divided by x cubed. I get 3x. Multiply that around, subtract, and already, right away, what remains is a lower power than what was on the bottom. So that's my remainder. I put that back over top of the x cubed plus 3x. Again, I'm stopping because the power minus 9x squared is lower than x cubed, so I've got a proper fraction. Well, I basically throw that proper fraction away, and my asymptote, which is oblique now, is the 3x. Y equals 3x is a straight line at an angle. It's got a slope of 3 after all. That is my oblique asymptote for this rational function. Alright, now graphing rational functions, there's like a 7-part step for you to follow on page 225. I don't really see any point in me typing it all out when you can just turn your book to page 225. It's very well described how to graph rational functions. It talks about finding your asymptotes and marking those, your x-intercepts, so on and so forth. But let me remind you, the steadfast way to find any graph is to make a table of values. You've also got a calculator at your disposal. You can use that in an appropriate way also. Let's take a look at our example now, an application, and this has to do with average cost. So it says here that the cost of printing X textbooks in thousands, so we're talking about printing thousands of textbooks, can be found with this function. They want us to find the average cost function. So whenever you're given a cost function, like we are here, to find our average cost function, we take that polynomial and we put it over x. So we are creating our rational function here. The little bar that we see over the C means average. So average cost is equal to cost divided by x. You need to remember that. So if I just put my polynomial over x, I now have my average cost function, and by the way, it's a rational function that's going to create a really cool graph that we've seen, or that we've seen stuff like. So here's a question. What is the average cost of printing 13,000 books per week? Well, what they want me to do is plug 13 into my average cost function. So I plug 13 in everywhere I see an x in my average cost. Notice it's down there on the bottom also. And I find out that the average cost to print 13 books is $35.18. What this means is each book cost the company $35.18 to print. Well, what would the average cost be for printing 25,000 books per week? So I'm plugging 25 into my average cost now. I get a much bigger number, $95 as opposed to the $35. So This is probably an important idea for companies. They want to keep their average cost low. Well, let's go ahead and use our graphing calculator to graph the average cost function. There it is. So I've started my x at 0 and I've ended it at 30. We'll talk about why I ended it in 30 in a second. I've started my y, that's my average cost, at 0, and I've gone all the way up to 100. Now the reason I chose those is based on the numbers that they gave me. 13 books, average cost was 35. 25 books, 25 books, average cost was $95. So that was kind of a guide to help me figure out what domain and range to use here. Now, makes a whole lot of sense based on what we did a little while ago. Let's use our calculator to find the number of textbooks that will minimize this average cost. So on this graph, I'm looking for that low spot right there. So I hit my trace button on my calculator and I move over to that low spot and I find out that it's 7.66 books. So they should make 7.66 books to keep their average cost the lowest. Now, what is their lowest average cost? Well, we can read that off right there also. It's $26.54. Alright, so we're all done. It's time for you to try some on your own. I'll see you in class and I'll see you online.